After this, just keep the door closed for some time.
Okay.
No, nothing is done. So just leave it. I'll have a look.
Do you need something?
No, that's fine.
That's a video on the
Yeah. So we are live streaming already. Yeah.
Yes. Yes.
Great. So hello, everyone. Good afternoon. It's just about 4, and it's time for us to get us started. So thanks a lot for joining us, and let us get the proceeding started by me inviting our Center Director, Professor Yashwant Gupta, to say a few words and kick this event off. So Yashwant, please.
Thank you, Dev. So dear colleagues and friends who've joined us today, on behalf of NCRA, it is my pleasure to welcome you to this year's Govind Swarup Memorial Lecture. We started this annual event 2 years ago to honor Professor Swarup, who passed away on 7th of September 2020. The inaugural lecture in 2021 was delivered by Professor Ron Eakers. The lecture for 2022 last year was delivered by Professor Richard Manchester. In addition to the memorial lectures, we had also been working on a memorial book on Govind Swarup, which contains a collection of memories and tributes to Govind that were sent in by colleagues and friends from all over the world at the time of his demise. Finally, after 2 years of delay, some of which I can ascribe to COVID, we have this memorial book now ready, and it will be available from next month onwards. You can see on the screen a copy of the cover page, and we will be sending copies to all those persons who have made contributions to the book, and we would be happy to have additional requests from others who would like to get a copy. Now, coming back to the memorial lecture series, our aim is to have a lecture by a prominent personality who has made an outstanding contribution to radio astronomy, be it in instrumentation for radio astronomy, or setting up of new radio astronomy facilities or experiments, or in research work in this field. And this year, it's a real pleasure to welcome Professor Martin Rees to deliver the Govind Swarup Memorial Lecture for 2023. Professor Rees, as you would have seen from the introductory material about him on the poster announcing today's lecture, is a highly accomplished and very versatile scientist. Further, and equally importantly for us, he had a long association with Govind Swarup. And I'll just show you one example, which is the picture which is there on the screen right now, which is the award ceremony when Govind Swarup received the Grote Reber Award. I think the year is 2007, and it's Professor Rees doing the honors. And this is something that Govind used to remember as one of the more memorable of his award that he had received. So I'm particularly grateful to Professor Rees for accepting the invitation to deliver this lecture today. It would have been even more wonderful if he would have been able to travel and be here in person to deliver the lecture, but that was proving difficult. But I'm sure that even in an online mode, we are in for a royal treat from the Astronomer Royal. So without much further ado, I hand it back to my colleague, Divya Oberoi, to formally introduce Professor Martin Rees and invite him to deliver the lecture. Thank you.
Yeah. Thank you so much, Yashwant. And it's really my very pleasant duty and an honor and a delight to introduce Professor Martin Rees. Professor Martin Rees is the United Kingdom's Astronomer Royal, as Yashwant just mentioned, and he's the 15th Astronomer Royal and was appointed to this position in 1995. He's based at the Cambridge University, where he's a fellow of the Trinity College, and he was also a former master of the Trinity College. He's a former president of the Royal Society, a member of many, many foreign academies, and a member of the UK's House of Lords. His research interests are also span a very wide range, all the way from space exploration to high energy astrophysics and cosmology. He has also served on many bodies connected with education, space research, arms control, and international collaboration and design. Sorry, just take a moment to mute a few people. Okay.
It is Siddharth, Divya.
Yeah, I'm trying to mute these guys. Yeah, apologies for that. Yeah. Okay. Okay, so in addition to his work on the academic side, on the research publications, he has also been very prolific writer for pop science and general articles. He has written about 10 books. The most recent of them are titled On the Future, Prospects for Humanity. There's another one with co-authored with Don Goldsmith, which is titled The End of Astronauts, sorry. And I believe the most recent one is If Science is to Save Us. So with this rather brief introduction to his many, many accomplishments, I invite Professor Martin Rees to deliver his lecture to us. His lecture, sorry, I omitted to say, is titled, How Did Atoms, Stars, and Galaxies Emerge? Astronomical Challenges for the Coming Decade. And with that, I'll stop sharing and I'll request Professor Rees to go ahead and share his screen.
Right. Yeah. Yes.
Perfect. So we can see you full
okay.
screen. Yeah.
Yes. Yes. Good. Good afternoon, everyone. I'm sorry not to be with you in person, but it's a great privilege for me to be asked to speak in honor of Govind Swarup. I was privileged to know him, and he was a remarkable man. He sustained his enthusiasm until his 90s. And of course, his achievements were great. 2 telescopes are his special monuments. The UTI, Lunar Occultation Experiment, which achieved arc-second resolution before interferometers could do that. And also, of course, the GMRT. Another wise strategic choice for India, because you could build it far more cheaply than any other nation could. So he left a wonderful legacy and is warmly remembered by so many of us around the world. And I'll be referring later to some of his later interests. But I'm going to start with some history for people who may not be specialists. And I'm going to start by showing a picture of Trinity College, Cambridge, which is where I've been based. And the best student we ever had here was this man, Isaac Newton. And as everyone knows, he taught us about gravity. And he wanted to think about space travel too. And this picture from the illustration to his famous book is very instructive. It shows cannonballs being fired from a mountaintop, and if it's fired fast enough, then the trajectory of the cannonball curves downwards, no more steeply than the Earth curves away underneath it. It goes into orbit. And I find this still the neatest way to explain to students the concept of orbital flight. But of course, Newton calculated that to go into orbit, you have to fire your rocket at 25,000 kilometers per hour, far beyond, of course, what the artillery of his time could do. And again, another historic thing, it was in 1957 that the Soviet Sputnik was the first object to achieve an orbit. And only 12 years after that, we had this iconic picture showing the Earth with its fragile biosphere being viewed from a spacecraft orbiting the moon, the sterile moonscape in the foreground. And then in 1969, we had the Apollo landings, and I treasure this picture, signed for me a few years ago by 7 of the astronauts who've walked on the moon. Human spaceflight has actually languished, but space technology, of course, has burgeoned. We depend on it every day for sat-nav, communication and environmental monitoring. And of course, we depend on space astronomy for the infrared, the X-rays, gamma rays, etc. And of course, for exploring the planets. In fact, planets have been explored close up by space probes. We've got close-up pictures of all the planets. Let me just start off with a sort of imaginary tour. Suppose you were launched into space and headed outwards in the solar system. Here's the launch. If you look back from about 10 million miles on your journey, you see something like this. This is the Earth and the Moon with the sun coming from the right. And then you would get to the red planet. And in fact, 40 probes have been sent to Mars over the last decades, including one from India and several from other nations. And some have, of course, landed. And one of the most recent is this, which is NASA's Perseverance, which is trundling around the surface of Mars. It's got enough artificial intelligence to be able to work its way around obstacles, but not yet enough to be able to do the geology by itself. But that will come maybe in 20 years. And this, incidentally, is a Chinese lunar Mars probe, which was launched at about the same time as Perseverance, and is about the same size. This is about the size of a small car. Going further beyond is Jupiter, the giant of a solar system, and this is a picture showing the weather near the North Pole of Jupiter. This is taken by a NASA spacecraft called Juno, and there are lots of cyclones, etc. And of course, we have close-up pictures of Jupiter's moons. These are the 4 classic moons found by Galileo. They've all been observed close up, and they're very different. There's a sorry. I just mentioned that there's a European spacecraft called JUICE, and that's an acronym for Jupiter Icy Moon Survey, which is going to Jupiter. It's being launched this week, and it'll take 7 years to get to Jupiter. And then it will look in particular at Europa, which is a moon that's covered in ice. Of course, we'd like to go still further to Saturn, and the Cassini spacecraft was launched in the 1990s towards Saturn and spent 13 years orbiting the Saturnian system and getting close-ups of some of its moons. And I'll just show one picture. This is a picture of the moon Titan of Saturn. It looks a rather nice place with little lakes and rivers, but the temperature is minus 160 degrees centigrade. and the lakes are lakes of liquid methane, so not a salubrious place for humans. And here's another Saturnian moon. This is a smaller one called Enceladus. This, like Jupiter's moon Europa, is covered in ice, and there's good reason to think there's an ocean under here, and sometimes spray is coming up through these vents. And NASA is planning to send a probe this far. And further still, this is a picture of Pluto, 12,000 times further away than the moon. A point I want to make is that these pictures of the outer planets were taken by spacecraft designed back in the 1990s, because they got several years to be built and then a decade on their journey. And if we think how much better mobile phones and things are than they were 20 years ago, think how much better we could do now in terms of sending flotillas of tiny spacecraft to the outer solar system. And indeed, as miniaturization and AI advance, there's less need for people. And as the introduction kindly mentioned, I wrote a book with a colleague, Don Goldsmith, saying that there was less and less practical case for sending humans, which is vastly more expensive than sending robots, because the robots will get more intelligent and they'll be able to do the kind of science of exploring, analyzing samples, etc. But just to digress a bit further, I rather hope that humans will, by the end of a century, have landed on Mars, but I hope they will be funded not by taxpayers, but by the billionaires. That's not only because it saves the rest of us money, but because billionaires, if they launch thrill seekers prepared to take high risks, can do things much more cheaply than a national space agency could, because the space agency would have to be very cautious in risking the lives of civilians, and therefore it would cost much more. So I think the future of human space exploration, at least beyond Earth orbit, lies really with the private sector able to send people prepared to take very high risks, even perhaps one-way tickets. And Elon Musk, of course, who is one of these people who launches private satellites, he says he himself would like to die on Mars, but not on impact. And he's, I think, 51 years old now, so 40 years from now, he might do this, and good luck to him. But I think it's important to say that I don't at all agree with Musk or my late colleague Stephen Hawking in thinking that mass emigration to Mars will ever be a way of escaping the Earth's problems. We've got to deal with them here. Dealing with climate change is hard, but it's a doddle compared to making the Martian atmosphere habitable. There's no planet B for ordinary risk-averse people. Well, of course, everyone is fascinated by whether there could be life on any other planet already before humans get there. And in our solar system, there's certainly no advanced life, but there is some genuine hope that these probes of Europa or Enceladus might reveal evidence of some primitive life in the oceans, which are on those satellites. So that'd be very exciting. But this whole subject was transformed by the discovery that most stars have planets in a retinue orbiting them. And this, of course, is one of the exciting new developments in astronomy in the last couple of decades. So let me say a little bit about this. Most of the exoplanets are detected not directly, but by their effect on the apparent brightness of their parent star. If a planet transits across the face of a star, then it blocks out a bit of its light, So if you're monitoring the star with very accurate photometry, you will see a dip when the planet goes across, and the dip will repeat once every transit, in other words, once every planetary year, the planet. And of course, the depth of the dip tells us the fraction of the area of the star which is obscured by the transit. For instance, if you were a long way away looking at the Earth transiting the Sun, the Earth's about 1% the radius of the Sun, so 1 part in 10,000 would be the depth of that dip when a transit occurred. But this spacecraft, called Kepler, spent 3 years looking at an area of sky about 7 degrees across and measuring the brightness of over 100,000 stars with the precision of 1 part in 10 to the 5th, looking for periodic dips like that. And it found that there were dips in most cases. It inferred that most stars had planets around them. And this is, of course, a remarkable discovery. And I won't be able to go through all the details, but the bottom left is a depiction to scale of all the planets found around hundreds of the stars Kepler looked at. I don't have time to go into this, but just to say that planets do seem to be ubiquitous among all the stars in our galaxy. And let me show this picture. This is my Cambridge colleague Didier Queloz, who was at Geneva, and this is the day he won the Nobel Prize for having discovered with his colleague Mayor at Geneva the first exoplanet back in 1997. And he was having champagne to celebrate winning the Nobel Prize. And he is now in Cambridge. He runs a group and has found hundreds more exoplanets and is studying what we might learn about whether they've got life on them. Let me just show you an example of one very unusual system that's been discovered. And this was discovered by a Belgian and British collaboration using a 22-inch telescope. They looked at a star and saw transits. And this is, as it were, a miniature solar system. The central star is an M dwarf, about the 10th the mass of the Sun, about 100th of the luminosity of the Sun, and it has 7 planets going around it, and the closest in orbits every 1.5 Earth days. So its year is 1.5 of our days, and even the outermost planet, this period is now known, and it's about 2 of our weeks. So this is a miniature solar system. But because it's around such a faint star, the outer 3 planets are in what's called a habitable zone, in that the temperature on them is such that water can exist, neither boiling away nor staying frozen all the time. And the other reasons for thinking that these planets aren't very propitious for life, but it illustrates the variety. And although it was detected with a small telescope, it was followed up, and there's no doubt about the data, because this shows a stacking of the observations of these stars, and you can see that this was done with the Spitzer infrared telescope, and you can see there's no doubt about the data, and you can infer the duration of the transits, etc. So there's absolutely no doubt that that system does have these 7 planets in it. Incidentally, just as a digression, because the system's so small, the planets are tidally locked, rather as the moon is to the Earth. And so if there were any intelligent life on these, on the outer planets in the TRAPPIST system, which is very unlikely, then to be 1/2 in the light and one half in darkness. So there'd be a kind of sort of a apartheid where everyone would be on the bright side except the astronomers on the dark side, in perpetual darkness. Well, let me now think about the future of this exciting subject of exoplanets. Up till now, we have essentially indirect evidence of these planets from transit observations, and in some cases from the wobble they induce in the motion of the star they're orbiting. But we'd like to see them directly, of course. And that's difficult. It's difficult because they are much, much fainter than their parent star. To take an illustration, suppose there were some aliens out there looking at our solar system, then to them, the sun would look an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, a pale blue dot, very close in the sky to its star, our sun, but a billion times fainter. But if the aliens had a big enough telescope to actually detect the light from the Earth, they could infer some things about it. They'd find the shade of blue was slightly different, depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer that there were continents and oceans. They could infer the length of our day. And by studying the spectrum of the light, they could infer its composition, its oxygen, and maybe they could perhaps infer there was lots of vegetation on the planet. Well, this is the kind of thing that we hope to be able to do in the next decade or two with regard to some of the Earth-like planets orbiting other stars. One instrument that will help, this is just a drawing of a telescope being built by the European Southern Observatory in Chile, which is unimaginatively named the Extremely Large Telescope, the ELT. And this instrument has a mirror 39 meters across, not one sheet of glass, but a mosaic of about 800 pieces of glass. And this will be able to collect enough light to be able to separate out the contribution from an orbiting planet and get at least a crude spectrum. Even before that time, it's possible that the it's possible that the James Webb Space Telescope will be able to do the same sort of thing. There's a trade-off because, as we know, it has greater sensitivity. It works in infrared, but on the other hand, its collecting area, being 6.5 meters in diameter, is far less than the ELT will have. But the quest for life in the universe, which is the thing that fascinates the public. I mean, I think all of us astronomers, if people know we're astronomers, the first question they ask is, are we alone? And it's rightly a fascinating question. We will have at least some clues, probably in the next 10 or 20 years. Because what we know at the moment is that almost every star has a planet around it, and roughly 1 in every 6 stars has an Earth-sized planet orbiting around it. So in our galaxy, there are literally billions of Earth-like planets, a large proportion in the so-called habitable zone. Incidentally, again, for historical digression, it's not surprising that planets are common. This is a cartoon which shows star formation, interstellar cloud contracting under gravity, and if it's got any angular momentum, it spins up and leaves behind a disk. And we see protostars, of course, which are orbited by disks, and those disks turn into planets. So we're not surprised. And again, another historical allusion. This is another quote from Newton. He thought it was a real miracle, a mystery, that all the planets were moving around the sun more or less in the same plane and in the same direction. He thought this must be providence that this happened. But of course, we now know it's a natural consequence of them having formed from a dusty disk spun off a contracting protostar. Exobiology is a subject which, of course, is of growing interest now that we have the possibility of observing places beyond the Earth where life might exist and might have formed. It's important that we don't know how life began. Even on Earth, we understand evolution from the simplest organisms to complex organisms, but we don't know what caused the transition from complex chemistry to the first metabolizing, reproducing entities we call alive. That's still a mystery. And of course, I like to say, and probably you'd all agree, that astronomy is a simple subject compared to biology. This is a picture drawn by Robert Hooke, who was Newton's least favorite colleague, who had an early microscope and produced a book in the 1660s called Micrographia, where he drew the things he observed. And this was a picture of a flea. And you can imagine what a inspiration it was for people to see the intricate detail of even such a small living thing as a flea. And we now know that all these things are so intricate and so complicated, far more so than a star or a galaxy. And that's a sort of modest statement I always make when talking to general audiences, that although it may seem ambitious to try to understand stars and galaxies, they are simple compared to even the smallest living thing. So let's go back to the simplicities of the inanimate world and think about stars and galaxies. We have learned, of course, in the last 50 years or so about stellar evolution, the life cycle of stars, and that's depicted here. This is familiar to the experts. I won't go into it. We know that the big stars evolve more quickly, are brighter, etc., and the low mass stars can last even longer than the sun will last. So it's familiar. And we see places where stars are still forming. This is a famous location where stars are even now forming. We see protostars with disks still around them. And of course, we see stars dying. This is what the sun will look like in about 6 billion years when it runs out of fuel. This is a planetary nebula blowing off its outer layers and will leave behind a white dwarf. And more massive stars live shorter lives and end more violently. And of course, here's the famous Crab Nebula, which was witnessed and recorded by Chinese astronomers. I guess the Chinese equivalent of the Astronomer Royal. He wrote to the emperor. I don't know if anyone in the audience knows Chinese, but this, I'm told, says that a guest star appeared, became brighter than the moon. And if one looks at that location in the sky now, nearly 1,000 years after this was written, it was written in the year 1054 AD, then we see the Crab Nebula. And of course, we have learned that phenomena like this are important. Indeed, we wouldn't be here without them. And the reason for that is something which was discovered at first by Fred Hoyle, but later by many other people. And that's that if you were to take a slice through a big star when it was running out of fuel, it would have this sort of onion skin structure where the outer layers would be still mainly hydrogen and helium, but the inner layers would be sort of cooked further up the periodic table. There'd be a shell of carbon and oxygen, and then neon magnesium, etc., etc., and then silicon, and then iron towards the center. And once you've made iron, you can't get any more nuclear energy, so the star faces a crisis, and then its core implodes and blows off the outer layers, and that gives you a supernova. But the important point is that the material ejected in the explosion, like we see in the Crab Nebula now, is contaminated with all the material that's been processed in the star during its lifetime. And so the interstellar medium is contaminated with these heavy elements, and then new stars form. So the wonderful story is that all the atoms that we are made of were synthesized from pristine hydrogen and helium in stars which lived and died somewhere in the Milky Way before our solar system formed, at least 4.5 billion years ago. We contain inside us probably atoms from hundreds of different stars that were spread through the entire Milky Way. This is a picture taken in 1971. And the people shown here are Margaret and Geoffrey Burbidge and Willie Fowler, a nuclear physicist from Caltech, and Fred Hoyle, who was one of my predecessors in Cambridge. And this was taken in Cambridge, actually, on Willie Fowler's 60th birthday. And he was a model train enthusiast, so that's the present that we gave him. But I show this because these people collectively wrote in 1957 a classic, very long paper, which is known in the community as B squared FH, after its four authors, Burbidge, Fowler, and Hoyle. And they tried to quantify how these processes could produce the different chemical elements and produce them in the observed proportions. Lots of carbon, oxygen, and iron, but very little of the heavier elements. So they were the people who told us that we are literally the ashes of long dead stars. If you're less romantic, we're the nuclear waste from the fuel that made stars shine. And I like this picture. Margaret Burbidge lived to be 100, and she died about 3 years ago. This is a picture of her receiving a birthday card on her 100th birthday. She had a wonderful life and was universally admired as one of the world's leading astronomers of her generation. And I won't go into this, but the scenario which B squared FH and their successors espoused was symbolized in this sort of flow diagram, that we have the Big Bang, which I'll talk about in a moment, and the stars form from clouds, and the low mass stars are still there. They last for more than 10 billion years, but the high mass stars explode as supernovae, throw processed material back into stars to form new generations of stars. Well, let's now extend our gaze beyond our own galaxy. This, of course, is what our galaxy would look like if you could get 2 or 3 million light years away from it and look back, a spinning disk viewed obliquely. This, of course, is Andromeda, our nearest big neighbor in space, which has in its core a black hole of about 30 million suns. And that's the typical galaxies. This is the Whirlpool Galaxy. And this is a picture, a survey, which shows the galaxies within about 400 million light years. Each dot is a galaxy, and this shows something which has been corroborated by much later data, which is that galaxies are, they're spread uniformly through space on a large scale, but they're concentrated into groups and clusters. We and Andromeda and 100 or so very small neighbors are in what's called a local group. And there's a Virgo cluster, which is much bigger, etc. So we know that galaxies are the dominant feature of the cosmic scene. How are we going to understand them better? Well, of course, astronomers are pretty helpless in that they can't do experiments. We can't crash 2 stars together for real, or 2 galaxies together to see what happens, as a particle physicist can crash together particles in an accelerator. But what we can do now is do these crashes in the virtual universe inside the computer. And let me just show you one example of a calculation of that kind, of what would happen if two galaxies collided. The calculation includes gravity and gas dynamics, and two galaxies are forming together, and they assumed to be two disk galaxies, and when they merge, they settle down into a sort of amorphous elliptical galaxy. I show this as a warning, because it's likely that the Andromeda galaxy will crash into our Milky Way, although not for 4 billion years or so. And what will happen then is that the disks of both those systems will be destroyed, and the solar system will still survive, but it will be embedded in an elliptical galaxy where there'll be no conspicuous disk anymore. Well, if you look out into space, we see some galaxies looking like this one. And having done simulations of the kind I just showed, we can infer that this system it involves two galaxies which have got dangerously close, so that one is pulling out a tidal plume on the other. And if you could come back in 100 million years, we'd probably see that these two galaxies have merged together, as in a movie. And of course, the other thing we can do with these movies is we can vary the conditions. We can put in different densities of gas and of dark matter and other ingredients, and to see which models the data best on the morphology of galaxies. Now, the other thing we can do, of course, in astronomy is directly observe the past and check our theories of galactic evolution, not just in the indirect way that a geologist or archaeologist can, but by directly looking back into the past, by looking far out to high redshifts where the light had to set out a long time ago. This is an example of a picture. This one was taken with the Hubble telescope, showing galaxies, many of them more than 10 billion light years away. So we see them when they're young. And so we have lots of data against which to test our theories of galactic evolution. And the James Webb telescope, which I already mentioned in the context of looking for exoplanets, is of course now giving exciting data on even more distant objects. And in fact, this week here in Cambridge, we have a conference where the people who are involved in these observations are all gathered together to present their new results and see to what extent they fit in with existing ideas of galaxy formation and evolution. This is one of the pictures taken with the James Webb telescope, and it extends the redshifts back to about 15. There was a claim of 18 in the early data, but that's a bit dubious. But certainly we're seeing galaxies the redshift of 13 or so, which means about tracing back nearly 98% of the time to the Big Bang. And there's a real richness of data because, of course, the images from the Space Telescope are much sharper, 10th of an arcsecond resolution. But let me just show this picture. This actually is an object that was detected with the Hubble telescope, but there'll be some better ones soon from James Webb. The object between the bars there has a spectrum shown here. This is a tracing of the spectrum. And the important point is that the strong emission line on the left of this picture, in the infrared at a bit above 10,000 angstroms, is actually Lyman alpha, the basic line in the hydrogen spectrum, which is normally in the far ultraviolet at 1216 angstroms. So this is an object with a redshift so large that wavelengths are stretched by a factor of a bit more than 8. So 1 plus z is 8, and so we're looking back a very long way when we look at this object. And this is incidentally such a good spectrum, because what we're seeing in this object is not the starlight, but the emission from gas in the galaxy, which hasn't yet turned into stars. And this gas is being energized and excited, not by starlight, but by a quasar, a central object, which outshines all the stars in the galaxy by a factor of about 100. The quasars were objects discovered in the 1960s, not well understood, but now they're generally agreed to be objects which involve very massive black holes of millions or even billions of the mass of the sun, which are energized by gas falling in and getting very hot. And this is a simulation of gas swirling into a black hole. And if the gas gets very hot and magnetized, then in being swallowed by the black hole, it gets very hot and luminous and produces an amount of luminosity outshining the galaxy. And so the brightest objects in the universe are the so-called quasars, where the light comes from massive black holes. And of course, the study of massive black holes is one which deserves several lectures by itself. But let me just quote a statement by the great Chandrasekhar, who was hugely impressed when black holes were discovered. Impressed especially because, according to Einstein's theory, which has been well validated, massive black holes are described exactly by equations we can write down. Indeed, equations that were invented by this chap here, Roy Kerr, who is still alive. He's a New Zealand scientist, and he produced a metric which we believe describes exactly a spinning black hole. And so what so impressed Chandrasekhar was realizing that the objects that were conspicuously detected in the form of quasars were objects which were standardized, almost as standardized elementary particles, just having two free parameters, their mass and their spin. And now, of course, it's a huge modeling study using computers as well to try and see if we can fit the detailed data on quasars and radio jets, of course, in terms of this model. And of course, it was the radio astronomers who first were able to detect evidence of this non-stellar activity. Well, let's now turn to cosmology, even further away from the present space and time. This picture was taken in the 1950s. It shows on the left a youngest version of Fred Hoyle, and on the right it shows Georges Lemaitre, who was a Belgian monk and physicist, and he was the first person to talk about the physics of a so-called Big Bang, hot, dense start to the universe. He called it a primordial atom. Fred Hoyle, of course, was famous in the 1950s for promoting a different theory, the so-called steady state theory, the idea that the universe had existed from everlasting to everlasting and had never changed in its gross properties. The galaxies were expanding away from each other, but new ones, as it were, formed in the gap. And this was a tenable viewpoint. And at the time that this picture was taken, there was no convincing evidence either way. Evidence came in the 60s that things in the past were rather different. In fact, the first evidence did come from radio astronomers. It came from the astronomers in Cambridge, who showed that if you compare the number of nearby and distant objects, bright and faint ones, there were more distant ones than there would be in a steady state universe, which implied that in the past, galaxies were more prone to the activity that gave them radio emission. So that was the first evidence against the steady state. And since I mentioned Uti and Govind Swarup, Govind with Kapahai, they wrote a paper where they plotted the number of radio sources against their angular diameter, which they could measure by lunar occultations. And they again found that there was evidence that there were more of these active objects in the past than there were today. But the clinching evidence, which made almost everyone believe that the universe wasn't in a steady state but had a hot dense beginning, came from these two people, Penzias and Wilson, who were radio engineers working at the Bell Telephone Labs in New Jersey, and they found that there was more background radiation in their detectors, which was just a nuisance to them really, than they expected. And they didn't realize what they discovered until other people told them. But other people suggested that what they had discovered was indeed something rather marvelous. It is what came to be called the afterglow of creation. And they found, and subsequent observations found, that this radiation filled all of space. It came more or less equally from all directions. And when it was observed at different frequencies, it proved to have a very exact black body thermal spectrum, indicating there was a relic of a stage when the entire universe was hot and dense, like the inside of a star, and the radiation was thermalized. But as the universe expanded, the radiation got diluted and cooled and shifted into the infrared and then the microwaves, but it fills the universe, got nowhere else to go, and this is there as the relic of the early stages of the universe, an early pre-galactic stage. And this led to the development of what's generally called the standard hot Big Bang story. And this time chart illustrates some of its key features, times plotted upwards, and the present at the top. And as we look back to the first stars in the first billion years, and we're now probing that in detail, especially with James Webb Telescope. As we go back into the past, the ambient radiation, which is now about 3 degrees, would go up. And a key time is when the temperature is not 3 degrees, but 3,000 degrees. And above that temperature, the gas gets ionized and opaque, like the inside of a star. And so that's what's called the decoupling. And so for the first 300,000 years, the radiation is trapped. But the photons that are detected in the microwave background, they have propagated uninterruptedly since the universe was a few 100,000 years old, since the temperatures of 3,000 degrees. So it's a probe of the early stages, the pre-galactic stages of the universe. And the other great triumph of the Big Bang theory is that if we are bold enough to extrapolate back to when the universe was a few minutes old, then its temperature would be high enough for nuclear reactions to occur. And they wouldn't produce much beyond hydrogen and helium and deuterium, but the proportions of those 3 light elements, which will be predicted to emerge as the material of the Big Bang cooled through temperatures of an MeV or so, would be about what is observed. Very good agreement, especially with deuterium and hydrogen and helium. So we have corroboration that we are justified in extrapolating back to when the universe was a few seconds old. And this is an amazing achievement. I miss. This is a movie. I missed this out. This is a movie which shows how, as the universe expands, the density contrast grows. If there's a region that's slightly above average in density, then that region will lag behind and condense out. And so if the early universe was not completely smooth, but had some regions of above average density, some below average density, then the above average density regions would lag behind, and they would eventually develop into stars and galaxies. Yes, okay, sorry. And to say a bit more about that, I realize I'm running out of time, but can I go for another 10 minutes? Okay.
Yeah, sure. Yeah.
Okay, yes. This is a picture of the whole skies in a projection. You're probably used to pictures of the Earth spread out to look like this. But if you look outwards and plot the sky in the same way, you find that the temperature is not completely the same everywhere. It differs from place to place by about 1 part in 100,000. And that's shown by these different colors here. So the temperature is different, and it's the overdense regions which are the ones which will eventually lag behind the expansion and form the cosmic structures. And what is remarkable is that if you look at the universe now and look at the root mean square fluctuations on different scales, it's smooth on large scales, etc., then you can predict what the fluctuation amplitude should be as a function of scale, and that's the solid blue line. But then we have data from looking at galaxies and clusters, etc., which fits very well. So it's rather remarkable that if you put into your computer a universe where the fluctuations have the properties which are observed in the microwave background, in that projection of the sky I showed you, and then run it forward, you get a universe which has structure as a function of scale, which is consistent with what is observed. So the universe is smooth on large scales, on small scales in the past and now, but quantitatively, the fluctuations in the past match the fluctuations today. If you imagine that the amplitude grows owing to gravity during the expansion. And I don't have time to go into it, but this, I think, is one of the most marvelous predictions in the whole of astronomy. This prediction was done by several people, which predicted the amplitude of the fluctuations in the microwave background on different angular scales. You can see this, it's in multiples, and on the top an angular scale. There's a big peak at 1 degree, and then some other bumps. And this is because in the early universe, there are sort of sound waves which oscillate, but then after decoupling, they're frozen in. And so you would expect that the spectrum of the fluctuations over the sky in the CMB temperature would be predictable. And what is amazing is that we have observations which are precise enough to give the dots in this picture. And it fits a theory, and from this theory you can calculate the fractions of baryons and dark matter in the universe. So I would say that the fact that you could predict this result is really an amazing achievement. Well, as I said, we can extrapolate back with some confidence to when the universe was a few minutes or even a few seconds old, because we have good evidence that the helium and hydrogen were produced back then, and the proportions agree with what you would calculate at the time. And we can calculate with some confidence what the Big Bang contents were like back to about a nanosecond. A nanosecond is the time when every particle has about the same energy that can be produced in the biggest accelerators, the LHC at CERN. But that's not good enough, because if you want to ask some fundamental questions, like what caused the fluctuations, why is the universe more or less smooth, but has these fluctuations? Why does it expand the way it does? Why does it contain the observed mix of atoms, radiation, and dark matter? We need to probably go back much further still. And here I put up a hazard sign, because here we become more speculative. As I said, we can extrapolate with some confidence back to a second, even a nanosecond. And after a nanosecond, the entire observable universe will be about the size of our solar system. But in order to answer those three questions, we need to extrapolate back much, much further still. And we have to have an idea, and one possible idea, still speculative, is that there was a period called inflation, which happened at an era of about 10 to the minus 36 seconds. And that's a time when the observable universe was not merely squeezed to the size of a solar system, but squeezed down to the size of a tennis ball. And then it's inflated very rapidly. This is a theory which was first proposed nearly 40 years ago. It's had lots of bells and whistles attached to it, but it's now taken quite seriously, but still it's based on uncertain physics. So you can make particular assumptions, guesses about the physics, and then work forward. And many of those guesses do lead to something called inflation, but it's still speculative. Just a digression, which I don't have time to go into. This shows a time chart of the universe going into the future, and the key question, which astronomers have wondered about since the time of Lemaitre and people in the 30s, is: will the universe expand forever, or will it stop expanding and recollapse? And that was not known. We now know that there's certainly not enough matter in the universe to make it recollapse, as on the left-hand side. It was thought until 20 years ago that we were in the middle time where the universe is gradually slowing down as the gravitational pull of every galaxy and every other galaxy decelerates the expansion. But it turns out that we're in one of the third type where it's now accelerating. And this was a big discovery, and it indicates that there's some extra force latent in the vacuum, what's called dark energy. And this force of dark energy is something which can overwhelm gravity and make the universe accelerate. I don't have time to go into this, but this just illustrates that if we are to explain the dark energy, we've got to understand empty space. It's energy and empty space. And that won't be done until we can understand things on the scale where quantum theory and gravity meet. And that scale is 10 to the minus 33 centimeters, 1,000,000 billion times smaller than the atomic scale. And this is just symbolic cartoons there. But what is believed by string theorists is that if you were to magnify a point of our three-dimensional space by that huge extent, then you would find that it is not just a point, but it's a tightly wrapped origami in 5 extra dimensions. And that's the kind of thing which we expect would need to be understood if we were to explain why empty space is able to exert this kind of force and actually exert a push which compensates on the cosmic scale with normal gravity. And if we look at the universe now, there's this famous pi diagram, which tells us what the universe is made of. And ordinary matter, baryons, is about 5%. Only a small fraction of that is actually luminous in stars. Dark matter, we don't know what it is exactly, is about 25%. But the so-called dark energy, this mysterious energy latent empty space, is dominant. I should mention that this diagram is often used to say that dark energy is the most important part of the universe to study. It's certainly most important for fundamental physics, but in terms of what's important for understanding the present universe and the structure of stars and galaxies, the dark energy is far less important than the dark matter. we can't understand why galaxies have the morphology they do without considering the dark matter, whereas the dark energy is not quite so important for the structures in the universe. Well, let's ask another fundamental question. How big is space? How large is physical reality? And the point I want to make is that there clearly is a horizon to our observations. And in the accelerating universe, there's a horizon in that galaxies that get beyond a certain distance disappear, rather like something that falls into a black hole disappears. But there's no reason to think that there's nothing out there, just as if you're on a boat in the middle of the ocean, you have a horizon around you, but you don't think the ocean stops just beyond your horizon. And so we suspect that the universe goes on much, much beyond our horizon. And so what we observe, the observable universe, is only a small fraction of physical reality. And we don't know how much further it goes. Most people say it goes at least 100 times further. It could go so much further that all combinatorial options are replicated. There were other, we have avatars out there duplicating ourselves. That could happen. And even that's not all, because all that would be the aftermath of our Big Bang. And the next big idea is that our Big Bang may not be the only one. And many versions of inflation have the feature which is depicted very schematically in this cartoon. In the bottom, that illustrates our observable universe and lots of galaxies beyond it. But that entire domain may be something which is just one bubble in an infinite ensemble. So the idea here is that there were many Big Bangs, and we are in the aftermath of one of them, but even that one could be much larger than the observable universe. And the main advocate of this idea is Andrei Linde, a Russian cosmologist now based at Stanford. And this raises another interesting question, which is that the physical laws and basic numbers are constant within our horizon. If you take the spectrum of a distant galaxy, then the atoms look the same, the spectral lines look the same. But there are some people who suspect that if we had different Big Bangs and set them all up, then they'd end up governed by different laws. In string theory, for instance, the 5 extra dimensions could wrap up differently in different ones. And so there's a possibility that physical reality contains the aftermath of Big Bangs, all governed by different laws of nature. And this raises another fascinating question, which is on the borderline of philosophy, but still really part of science, which is which version of this decision tree is correct? How many Big Bangs were there? Was it just one, or were there many? If there are many, are they all governed by the same physical laws, or not? If they're governed by different physical laws, then of course we can ask the question, would they all be propitious for the existence of stars, the origin of galaxies, or above all, the origin of life? And there's an idea called anthropic reasoning, which is the idea that there's some of these universes which aren't propitious for life, and we're in one that is. And this explains the sort of fine-tuning that some people are about. It seems to involve fine-tuning that our universe does allow gravity to be weak enough for stars to exist, and allows chemistry to exist. And this is I think it's a scientific question, though still a very speculative one. Let me just mention 2 or 3 things we have to worry about. This is a famous pedagogical diagram, which Bernard Carr and I, 40 years ago, many others have, which shows a mass upwards and radius, and it plots on this picture black holes there, and photons, Compton wavelength of going the other way, and object of nuclear density, object of atomic density. And you can see, if you look at the atomic density line, you start with an atom, you get roughly solids, you get humans, then you get the Earth, and when you get up to the size of Jupiter, gravity starts crushing you, and then you get to the domain of stars. And the fact that stars are so big compared to atoms is because of the scale on the left-hand side here. The fact that gravity is about 38 powers of 10 weaker than the microphysical forces. And so it's because gravity is so weak that objects have to be so big compared to microscopic scales in order to be held together by gravity. And also that the universe can last so long. So it's necessary for gravity to exist, but to be very, very weak. For this very large number, 10 to 38, to be so large. If it's a bit larger, then it would be possible to have an even more interesting universe. But if it was smaller, then objects the size of us would be crushed by gravity, and stars would be very small and wouldn't last very long. A second thing, I mentioned that the universe is not completely smooth. It has structures in it which develop into galaxies. There's a basic number Q, which is the amplitude of those fluctuations. It's the temperature fluctuations over the sky in the microwave background pictures I showed you. And the size of the amplitude of those fluctuations determines how early in the universe bound systems form and how large they are. We could have a rougher universe or a smoother universe. And let me just mention what the universe would be like if Q was 10 to the minus 6. If that was the case, then it would take a very long time for gravity to grow an initial small perturbation into a galaxy, and it would be a very, very shallow potential well. On the other hand, a universe where gravity was 10 times stronger, so when the fluctuations were 10 times larger, would be rather more interesting than ours, because instead of galaxies condensing out now, things the size of Coma cluster would condense out at a rate of 10, and you'd have enormous disk galaxies formed there. And this might be an even more propitious universe for life in. But on the other hand, if Q was too large, more than 10 to the minus 3, then we would have big black holes forming. And we wouldn't have a uniform universe. If you like, the difference between a mountain landscape and an ocean seascape. In the ocean, even the biggest waves are small compared to the horizon. But in a mountain landscape, one feature can dominate the view. And if Q gets very large, then you can't use the standard cosmological model anymore, and it becomes more complicated. So Q is in the middle range. It couldn't be less than 10 to the minus 6, couldn't be more than 10 to the minus 4 if galaxies and stars were to exist. And let me mention just a third kind of universe that I've thought a bit about, called the nuclear-free universe. Suppose you had a universe like ours, but suppose you switched off the strong interactions, so just protons, just hydrogen. Then, surprisingly, you'd still have galaxies forming, and you'd still have stars forming, but they contract on the Kelvin time scale, just releasing gravitational energy until they form white dwarfs or black holes. And so on a large scale, this nuclear-free universe would look like ours, but it would bear the same relation to the actual universe that a marble statue does to a real human being, in that you could have no complicated structures with no chemistry, but you could have a universe of galaxies and stars. And no life, probably, no chemistry, except maybe if you've read Fred Hoyle's classic book, The Black Cloud, which is complicated magnetic structure in the big cloud. That's the only kind of intensive life you could have in this universe. Well, I've strayed too far into science fiction in talking about these very speculative ideas, which are going to take many decades to firm up. But I don't want to leave you with this flaky note, so let me just finish with one more slide, just to address something particularly to the younger people thinking of a career in astronomy. When Swarup and I started, new things were happening. So it was great to be a young astronomer because the experience of the old guys was at a heavy discount because there were new things that we could all think about on a level playing field, as it were. But the same is true now because let's remember that we've got new instruments. We've got the James Webb Space Telescope. We've already got ALMA, and being built are the ELT and a square kilometer array and 2 large X-ray projects. And so there's a huge scope for much larger data. And of course, we have much more computer power to analyze these things. So I would say we are going to have a hugely exciting decade to come. And I think we should look forward to that and encourage younger generation, but they will need to learn some chemistry and some biology because there's going to be linkage between exoplanets and exobiology, and also maybe some new physics is going to be needed to understand the very early universe. And I finish up with a quote from Edwin Hubble, very heavy smoker, as you can see by that picture. He said, only when the empirical resources are exhausted should we move on to the dreamy realms of speculation. Well, I've done that a bit in this talk, but I think it's important that astronomy is a data-driven subject. Theorists have only contributed 5%, and 95% has come from the instrument builders and users. And that's what Hubble thought, and I'm sure Govind Swarup would have agreed with Hubble. So let me finish with that. So thank you very much indeed for listening.
Thank you so much, Professor Martin. And I applaud on behalf of all of us. I'm afraid it's a virtual applaud. Yeah. Yeah.
Right.
Thank you so much. So if you have a bit of time, maybe we can take questions from
yes,
the
indeed.
audience.
I'm sorry I talked for so long, but I'm certainly happy to answer questions.
Perfect. Yeah, thank you so much. So let's first go to the audience on Zoom.
Let me. Can I just unshare my screen?
If you prefer, yes, you could do that.
Okay. Yeah.
So, folks on Zoom, if you would just raise your hand, then we can take questions one by one. And I request the audience who has joined us on YouTube Live to please type their questions in the chat box, and I'll take a look at them and pick a few. So let's go to the live audience on Zoom first. Yeah. Okay, I don't see any raised hands just yet. Let me look at the YouTube window for a moment. Questions. Okay, so there are a few questions on the YouTube chat. I'm not sure how pertinent they might be, but let me ask at least one of them. So this is from Mr. Raghav Manchanda, who asks how to calculate how many atoms are present in any celestial body. How would you respond to that? Yeah.
Yes. Well, should be quite easy, really, because we know from chemistry and physics the mass of a single atom, and we know also the mass of the Earth, the mass of the Sun. We know the mass of the Sun from prime Newton's laws of gravity, and so one can calculate the number of atoms. And the number of atoms, for instance, in the Sun is about 10 to the power 57. And that was implicit in one of the diagram I showed towards the end, which showed masses against radii, and all stars have that sort of mass. So it's one thing you can quite easily calculate. What we can't calculate is extreme conditions when you don't have ordinary atoms. You have the atoms torn apart, and you only have their internal structure, which we don't understand so well. But the number of atoms in a star, or indeed in a human being, is something which is quite easy to calculate.
Right. Indeed. In fact, something which you said relates to the next question which has appeared, which is what's inside a black hole here?
Yes. Okay. Well, of course, a black hole has a sort of a surface which things can fall into but can't come out of, and so we don't know what's inside. But there is a theory, a view that inside the conditions get so extreme that we need some uncertain physics. We get near to what's called a singularity. And so we believe that near the center of a black hole, the conditions are really like in the very, very early stages of the Big Bang. And we don't understand either of those. But we have some clues because Einstein's theory, although we can't test it inside black holes, has now been very well tested outside black holes. As one knows, it's very well confirmed. And so we take seriously what it predicts about the inside of black holes until it gets very, very extreme. And I mention that point because in discussing what I call the multiverse, or the parts of our universe which are beyond our horizon, some people say it's not just metaphysics. You've got to be able to observe things for it to be part of science. And I will give a counterexample to that, which is that what you need to do is to have enough evidence for a theory which you can observe, to have confidence in it. And you can then take seriously predictions it makes in places you can't observe. And for the inside of a black hole, which we can't observe, we can take seriously what the Kerr black hole model and things like that say about what's there, because it's based on a theory which is well confirmed in other contexts. And in the same way, I would argue that the question of whether there are other Big Bangs, although it's entirely speculative, is something which is part of science. It's speculative science. And if I could mention a small anecdote, I was on a panel more than 10 years ago with Andre Linde and others, and we were asked by the chairman, how likely would you rate the existence of a multiverse to be? And how would you do it on the scale? Would you bet your goldfish, your dog, or your life? And I said I would almost bet my dog. Linde said, well, he'd spent 25 years on this theory, so he'd almost bet his life on it. And when told afterwards about this episode, the great physicist Steven Weinberg said he would be happy to bet Martin Rees's dog and Andre Linde's life, which he takes the multiverse quite seriously.
Thanks a lot for that anecdote. Yeah. There's another question, which is, I think, something which you have written extensively about, which let me take up. So sorry, I'm trying to get the name of the person who posted the question. Just a sec. Okay, sorry, it's just outside my Zoom window, can't get it yet. So why missions to send humans to space have not been possible even after decades of the first Apollo mission? And there's a second part to that question. Is it necessary to get ready for being able to colonize some other planet here?
Yes. Well, I think, I'm old enough to remember the first moon landings, Neil Armstrong's one small step. And at that time, I and many of us thought it would only be another 10 years before there were footprints on Mars. But because, as we know, that remains more than 50 years later the high point of human space exploration. No one has been beyond low Earth orbit since then. But the reason, of course, was that huge funds, nearly 4% of the US federal budget, was spent on the Apollo project in order to beat the Russians. It was superpower rivalry, not science nor anything commercial, which drove that. And having beaten the Russians, there was no motive for that huge extra expenditure. And so that's why human spaceflight hasn't gone beyond low Earth orbit. But I think also, and discussed in our book, as robots can do more, then the practical case gets less. but as I said, I think that it's going to be very hard to justify sending people to Mars because it's very dangerous, very, very expensive. You've got to bring them back and send to Mars the equipment for the return trip. So the return ticket's 10 times as expensive as a one-way ticket, and so I think it's going to be very hard to justify taxpayers' money. So I do think that it's possible that a few people will go as adventurers, just like they do dangerous sports and things, and we should cheer them on. But I don't think it'll be ever a planet B for ordinary people. And so I think the idea that we have to plan to escape the Earth by mass emigration is a dangerous delusion. We've got to sort out things on the Earth, use our science in those directions, and accept that it's the only habitable planet we ever have. Maybe in the far future, there will be entities that will be able to go through the universe, because, of course, one thing we should remember is that astronomers can't take seriously the idea that we humans are the culmination. We know it's taken 4 billion years for us to evolve from simple life, but we know also that the solar system has 6 billion years ahead of it, and the universe may be almost infinite amount ahead of it. And to quote Woody Allen, eternity is very long, especially towards the end. And so we are maybe a halfway stage, but we may be a rather critical stage. We may be a stage when, for the first time, flesh and blood entities are superseded by electronic entities. That's certainly a possibility. And if that happens, that would, of course, allow our post-human descendants to live on Mars, and perhaps if they're near immortal, to embark on interstellar voyages, which are never going to be feasible for human beings. So I think for human beings, flesh and blood, I think this Earth is the only habitat we could ever have.
Yeah. Thank you so much. Thanks. That's, to me, it's a very convincing answer, and I think along the same lines.
Yeah.
Okay. Okay. So we don't seem to have many other questions. So let me thank you for such a wonderful lecture covering, an enormous range of subjects, all the way from solar neighborhood to exoplanets to future of space exploration, and the origin of life beyond Earth, all the way to the fundamental and perhaps speculative questions which stare us in the face. Yeah. So thank you so much. But I'll invite Professor Yashwant Gupta, our Center Director, to offer the formal vote of thanks to you.
Yeah, thanks, Professor Martin Rees, for a very wide-ranging lecture, which is what we would expect from somebody like you, covering the entire span of things that an astronomer and even philosophers may want to think about. So it was wonderful to have you, and thank you once again. Thanks also to the organizing team from NCRA, which helped to put together the event for today. So thanks everybody, and we can then formally close the event. Divya, unless there's anything else to be added?
Nope. I was just going to thank the audience, people who have joined us online on YouTube and on Zoom, and of course our IT team, which helped us put this event together, and it worked flawlessly. So thanks everybody for all your help and support, and of course a special thanks to Professor Rees. Yeah. Thank you so much.
Thank you for the invitation. Thank you for listening, and it's been an honor to speak in memory of Govind Swarup.
Thank you, sir.
Thank you.
Okay, so I think with that we can formally close the session. Yeah. Goodbye, everyone. Yeah.
Goodbye.
Yes.